Hello, here we have another workshop exercise of geotol playbook, and here in this exercise we have to find out this maximum and the minimum distance of the cam wheel, and the drawing is here. So to get the distance from here to here, first we will find out this distance from here to here, and for this we will subtract this 12.5 from this 55, and we get 42.5. And then the profile tolerance is given here, which is of zero point 0.4 with datum B and A. So we will subtract this 0.2 from this 42.5 to get the minimum value from here to the center point. So 42.5 minus zero point 0.2, it gives us a 42.3. And for the next distance, which is from here to here, this one, the radius is given, which is of 25, and the profile tolerance is here, which is in this DRF zero point 0.2 U in a circle and then 0. So it means this profile tolerance is unequally distributed inside and outside. So zero point 0.2 is inside and the outside profile tolerance is 0. So we will subtract this zero point 0.2 from this 25, and we get this 24.8. So it's 24.8, and when we add both these two value, we will get the minimum distance from here to here. This summation of these two value is 67.1. Yep, it's 67.1. And for the maximum value, again we subtract this 12.5 from 55. We get 42.5, and we gonna add this zero point 0.2 tolerance, which is of profile tolerance. So 42.5 plus zero point 0.2, it's 42.7. 42.7. And the next distance from here to here for the maximum value, the radius is of 25 and the profile tolerance is 0. For the outside profile tolerance, it's here 0. So 42.7 plus 25, and it will give us a value or size from here to here. The maximum size, it's 67.7. So the maximum size is 67.7. Then in the next few line bracket in this drawing, we have to find out this minimum and maximum number 3 and 4. For this, we could go with this dimension, which is of 24, and from this point to the next point here, it is of radius 5. So 5 plus 5 plus 24. So 29 is the basic size, and we have a profile tolerance given here, which is of zero point 0.2 with the maximum material boundary, datum B. So datum B is here, which is a position of a hole. So when the hole is at MMC, then this datum B is maximum at the maximum material boundary here. So this profile tolerance not gonna affect this total distance from here to here. We are calculating this number 3 and for the maximum and minimum value. And this profile tolerance would affect, which is of 1, with datum A and B at maximum material boundary on this side. So 5 minus 0.5, and again for the upper side 5 minus 0.5 plus 24. This will be the minimum distance from here to here. So 24 plus 5 minus zero point 0.5 plus 5 minus zero point 0.5. So 4.5 plus 4.5, 9 plus 24. So the minimum value is 33. And for the maximum value, this 24, then 5.5 plus 5.5 plus 24. So 11 plus 24. And this value is 35. So the maximum is 35 and the minimum is 33. And for this section of your line bracket, number 5 and 6, we know the basic size is 10, 5 plus 5, but the profile tolerance on both those sides are different. Here, this on the upper side it's zero point 0.2 and the downside is of 0.1 of 1. So the 5 minus zero point 0.1 and 5 minus zero point 0.5, it's 4.9 plus 4.5. Yeah, the minimum value is 9.4. Yes, it's 9.4. And the maximum value, which is of 5 plus 5, then zero point 0.1 and then zero point 0.5. So 10.6. Then in next infill line clamp for this width, which is 7 and 8th number. The drawing in the drawing, it's a radius of 5 and the 5. So the radius is 5 plus 5, 10, and the profile tolerance is given here, which is of 1.5 all around, with the maximum material boundary of datum B. So datum B is here again, this hole, the position of this hole. So 5 minus 0.75, then plus again 5 minus 0.75. So it will give us a value of 8.5 for the minimum value. So the minimum is 8.5 and the maximum value is 5.75 plus 5.75 for both the sides, and it's 5.75, 5.75, so 11.5, maximum is 11.5. So it's this value is 11.5. Then for this 9 and 10th number, it's here, this one. From A to B, the profile tolerance is of 0.5 with the same maximum material boundary, and this radius is of 4. So 4 minus 0.25 for this side and 4 minus 0.25 for this side. So this total will give us 7.5 minimum. Okay, mm, just here. 7.5 is minimum. And the maximum is of plus 0.25, then 4 plus 0.25. So 8.5 is the maximum value. And then here this minimum and maximum values for from here to here, this one. So it's zero point 0.5 of a profile tolerance with datum A, and the radius is of 4. So 4 plus 4. Okay, we are going to calculate this one. This 4 and 5, it's 9. And we have to add this one, which is of 1 plus 1.5. So for the maximum, this 4 plus the 5, 9, plus this 1.6, plus this 1.6, and the profile tolerance, which is of 0.25. So it will give us a total of this is 1.6 plus 0.25, 10.85. So the maximum value from here to here, this is 10.85. And this minimum value is 5 plus this 4, and 1.5 minus zero point 0.1, so 1.4. So 9 plus 1.4 minus this 0.25 profile tolerance, and it's 10.15. So the minimum value is 10.15 here. So here the next is the hatch bracket, and again here we have to find out these values, maximum and minimum. So for this first one, the maximum value or the minimum value from here to here is from this point to this point is 37. So we got here this 37, then plus 6 and 6 here. So 12 plus 37, and the profile tolerance is given here, which is of 1.5, with the same maximum material boundaries with datum B, and datum B is the position of this hole here. So it's a all around profile tolerance, which is of 1.5. So it means 37 plus 6 plus 6 minus 1.5 for the minimum value, and the minimum we get say 47.5. And for the maximum value, it's 6 plus 37 plus 6, 12 plus 37, and which is 49, then plus 0.75 and 0.75. So the maximum is 50.5. For the second, we could go here with this dimension, which is of 65 here. So 65 minus this this 1.5 for the both sides, and the 65 plus this 1.5 for the both sides will give us the minimum and the maximum value. So for this minimum value, it's 65 minus 1.5, we get 63.5. And the minimum values are here, which is of 65 plus 1.5, 66.5. Then for this third number, it's here this distance, which is of inside distance, and the profile tolerance on inside surface is of 1 with atom A and B at maximum material boundary. So in this it's a free state modifier, and the profile tolerance is of zero point 0.5 on this phase. So for this third number, it's 35, and the minimum value is 35 minus 1 for the both sides. So the minimum is 34, and the maximum is 35 plus 1, which is 36. Then for the fourth number, it's here this one 17. So the dimension is 17, and the profile tolerance on this length is here this 1. So 17 minus zero point 0.5 will be the minimum. It's 16.5. So it's at fourth number. It's 16.5. 16.5 I'm writing here for the fourth number. And the maximum value is 17 plus zero point 0.5. So it's 17.5 maximum. And then for this number 5, the dimension here it's 32, and the profile tolerance is zero point 0.5 on this face, and the profile tolerance of 1 on this face. So 32 minus this 0.25, then minus zero point 0.5. So the minimum is 31.25, and the maximum value is 32, then plus zero point 0.5, then plus this 0.25. It's 32.75. 32.75 is the maximum. So in this profile stacking problem, so we have to find out this maximum and the minimum distance. So for this distance from here to here is 40, and the profile tolerance is here this one profile of 1. It is this side of parting line. It means at the downside from this line. This profile tolerance, and the upper side we have this profile tolerance. For the maximum size or minimum size from here to here, we will subtract this 40 minus 1.5 divided by 2, or it will be 38.75, the minimum value 38.75. And for the maximum, uh, this 40 plus this 0.75 plus this zero point 0.5 of this profile tolerance, and the maximum is 41.25. So the maximum will be 41.25 here. Then the total dimension, which is from here to here, this one, the maximum and the minimum. Uh, the minimum distance from here to here is of 35, which is given here. This one is 35 plus this 11. So 35 plus 11, it's 46. And from this 35, we have the profile tolerances of 1.5. So we will subtract 0.75 from this 35, and then plus from this 11, we will subtract this 0.05, which is the profile tolerance here at the bottom side. So 35 minus 0.75, it it gives 34.25. So it's 34.25, and 11 minus this zero point 0.5 profile tolerance. So it's 10.05. Oops, 10.5. So it's 10.5. So it's 44.75. So the minimum value is 44.75 here. 44.75. And the maximum value is this 35 plus 11, then plus zero point 0.5 plus 0.75. So the maximum will be 47.5. So it's 47.5 here. Then this one 18, the maximum and the minimum from here to here, this one. So for this, we will subtract this 1.5 profile tolerance. It's on this side also. So 18 minus 1.5, it is 16.5. It's our minimum value. This 16.5 here. And for the maximum 18 plus 1.5, we will get the maximum value, which is 19.5. This one here, 19.5. Then for this next, which is a 10 plus 17 plus 10, the profile tolerance is of 1.5, 0.75 from here and 0.75 from this side. We could subtract this 1.5, and we could add in this basic dimension to get the minimum and the maximum values here. So the minimum value is 10 plus 17 plus 10 minus 1.5. So it's 37 minus 1.5. The minimum value is 35.5. And the maximum value is 10 plus 10 plus 17. 37 plus 1.5. The maximum is 38.5. It's a maximum value here. This 38.5. Then this dimension, which is of 24 here, um, which is of 24 minus 0.75, which is here, this profile tolerance. So 24 minus 7 minus 0.75 will give us this minimum value, which is equal to 0.75. And we will subtract this point, zero point 0.5 from this value also. So it's double 2.75. And for the maximum 24 plus this 0.75 plus this zero point 0.5 for the bottom side, this profile tolerance for the maximum value. And when we add all these values, we get this 24 plus 0.75 plus point 0.5, 25.25. Yep, it's 25.25. Then for this maximum and minimum value, this one, um, it's 35 from here to here. Then minus this 27. So I get this value of 8 when we subtract this 27 this from this 35. So it's 8. The basic size of 8, it's here. And I will subtract the profile tolerance here. So for the minimum value, I will subtract this 0.75 from here and 0.75 from here. So it will give me a size of 8 minus 1.5. So the 6.5 is the minimum value here. So it's a 6.5 minimum. And the maximum values is 8 plus 1.5. So it's a 9.5, the maximum value. Then here in this one, the maximum and minimum value for this distance, which is of 21. So the profile tolerance is of 1 on this side. So 21 minus 1, the minimum is 20 and the maximum is 22. And similarly for this side, the size is of 33. 33 minus 1 will give us the minimum value, it's 32. And this total 33 plus 1 is 34 maximum value. Then it's a similar, the same kind of problem, profile stacking problem that we have done before. And the next on this side, on the part below, apply position control to allow the holes to move zero point 0.4 side to side, but only zero point 0.4 in up and downward direction. So there are two ways to define this one. I can say this side, this position tolerance on this side is of 0.1, 0.1. Uh, it's up and down tolerance, and the side by side tolerance we can show here. This one like this, it's a zero point 0.4, the side by side position tolerance. On the part below, show the size and shape of the tolerance zone that were defined on the previous time. Okay, the size and the shape of the profile tolerance zone is like this one. This side is of 0.4 and this side is of 0.1. Then we have to define the datum feature reference here. So for this 0.1, I can show like this. The first is symbol of the position. So it's a symbol of position, and then 0.1 tolerance with the maximum material condition. with datum A and B and C, with A and B and C, so on. And similarly, the profile tolerance shown this point 4, we can show the datum reference frame here on this side of this position point 4. Then what is the perpendicularity tolerance for the three holes in relationship to datum A? So datum A is here, this one, the flatness of the face. This is the datum A, and B is here, C is here. So for datum A, we have two tolerance here, which is of a point 0.4 side by side, and the point 0.1 is in up and downward direction. So perpendicularity tolerance we can define, which is of point 0.1. Our perpendicularity tolerance can move within this tolerance zone, which is a point 0.1. Then here in this exercise, on the rectangular hole in a part below, apply profile tolerance of point 0.1 all around to control the size and shape. In addition, apply position to the hole within of point 0.5. Boundary at MMC in relationship to datum A, B, and C. And for this, first of all, on this rectangular hole, it's a all around symbol, and the profile tolerance I can apply like this. It's a profile tolerance symbol, and the profile tolerance is of point 0.1, and with respect to datum A. And then for the position for these holes, uh, this is the symbol of position. Then the tolerance is in diameter, which is of point 0.5 at mmc. So we will add the maximum material condition, the symbol of mmc, and with datum A, and B with maximum material boundary. So B it with the maximum material boundary. So this M in a circle. So it's M, and then C, and the again maximum material condition M in a circle, maximum material boundary, and then we can define this datum reference frame to this hole. And for this MMB, which is of 40, it's given here, this 40, and we will subtract the profile tolerance, which is of point 0.1. So point 0.1 at this side and point 0.1 at this side, 0.05 at this side and 0.05 at this side. So the total is of point 0.1. So 40 minus point 0.1, this MMB is 39.9 here. It's 39.9. And on this side, the size is given, which is of 20. So from 20, we will subtract the same point 0.1. So 20 minus point 0.1, this MMB is 19.9. This MMB is 19.9. And here we have to tell this composite position frames, what it means with the upper segments and the lower segments. So this upper segment of this DRF, composite DRF, is known as a pattern locating tolerance zone, and normally we call it with a P pattern locating L P L T tolerance John, pattern locating tolerance John, and FO feature. So PLTZF, it refers to the first frame, and the lower frame is we call it a feature relating tolerance zone. FRT, feature relating tolerance zone feature. So FRTZF for the lower segment, and the lower segment controls the rotation and the features of the part. If we don't have any datum features with the lower segments, then it can rotate, it can tilt and shift. So the lower segment is for position, we can say, and the upper segment is for location and the rotation and the orientations we can use for the upper segment. And if we have two single segments of this DRF like this, then the upper segment controls the location and orientations, and the lower segments controls the rotation only, like perpendicularity and the parallelism and the angularity we can control with lower segments. And then here in this next drawing, the three functional gates below can be used to verify the three segment position specification that's shown in earlier in this units. Okay. Then they calculate the pin size and three gauges to help explain the call out. So here is the drawing. So we have to tell the meaning of these three different call outs. So the first one call out is not stopping this datum A is here, this one on this face, and datum B is the position of the central hole, and datum C is the position of this gauge block. So at the maximum material boundary of the gauge block and the maximum material boundary of this central hole, and the position of these holes, it means the first call out is not stopping this rotation and the translation with datum A, B, and C. These holes can rotate like this. They can rotate. So this call out is for this just the size and the location, but it not stopping the rotation, and they can shift up and down. So for this the gauge block maximum material boundary will be 10. The size is here this 10 minus the position tolerance we got here, which is 0.85. So 10 minus 0.85 will give us a 9.15. So the gauge block maximum material boundary is 9.15 here in this call out, and the gauge pin virtual size is 13.35 minus 0.85, and we get the size of 9.5 here. And this gauge pin RMMB, it's 15, and the perpendicularity tolerance is 0, so it's 15 here. Then the second is call out. It means it stops the rotations with this position tolerance of 0.25 with datum A and B with the maximum material condition. So it will stop the rotation with datum A, and when B is at the maximum material condition. So this hole won't rotate in this direction, in both these two direction. And here the gauge pin virtual size is 10.35 minus 0.25. So this will give us a size of 10.1. And the gauge pin at maximum material boundary, It will be 15, the same 15 answer. Then for this third call out, which is with datum A only. So with datum A, we can stop the perpendicularity. So this call out stops the perpendicularity uh, with datum A with this holes. So the gauge pin virtual size here will be this 10.35 minus 0.12, so 10.23. So gauge pin size is 10.23, and this call out stops the perpendicularity. And then in this workshop exercise, before any geometric control applied, what is the coaxiality tolerance in between the diameters? For the coaxiality and the concentricity, both are same. The concentricity and symmetricity are not in use after the ASME 14.5 2018 standards, and the drawings which are based on GD&T after 2018, you couldn't see this to tolerance, the concentricity and symmetricity. And the reason is of removing these two symbols, concentricity and symmetricity, from the this GD&T for revolve based part feature like this. It's a revolve feature based part, and to refine the datums. Datums plays a very important role even in the machining as well as in the inspection. So datums plays a role everywhere, inspection and in machining. For these types of revolve based part feature, if I say it's my datum A, and it is on its central axis. The central axis is my datum feature, primary datum feature, and from this feature, for the concentricity, I have to find out these opposed points either in ID or OD. So this thing is kind of impossible in real practice when we capture this pass in lathe and revolve it while touching the dial on its OD or either in its ID. We are actually finding out the circularity and the run out of this part, but not the concentricity and symmetricity. Um, the same is for the rectangular blocks or square blocks. This center plane is the datum plane, and we find out the opposite points, which is hard to imagine the center plane in its center. It can be here, it can be there. So it's a little hard to imagine the central axis as datums. So that might be the reason they removed these two symbols from ASME Y14.5 2018. But still in ISO 1101 or in GPS, we are using these two symbols, coaxiality, concentricity, and the symmetricity. And I'm not a GD&T expert. There might be some other regions. We are not using these two symbols uh, in drawings based on GD&T. So here, before any geometric control applied, what is the coaxiality tolerance? Here, I can say on these two diameters with this datum A, the central axis, it's 0.05 here, and the same here, the 0.05, and I can say it's zero point 0.2 here on this diameter. Then on the part above, apply datum feature symbols to create a datum axis A and B by using the right and left diameters. So it's here the same, the central axis is the datum A. Apply a position coaxiality between the right and left diameters of point 1. Okay, so for this I can say this size is my datum B, this one, and here I can define a coaxiality tolerance of zero point 0.1 with datum B. Then next apply a position tolerance to the large center diameter within a diameter of zero point 0.3. So for this I can say it's a position symbol. First is the position symbol and then the tolerance is of zero point 0.3 with the it's a central axis defined as a datum A. So the primary datum is the central axis. So this is the datum reference frame. Like this we can define here. Then the next is calculate the virtual size for the right and the left diameters on the virtual case below. So it's 9.5 plus zero point 0.5 on this side. So it's 9.6, and here it's 6.35 plus zero point 0.1. So it's 6.45. Then to define the datum axis A and B, do the datum feature simulator collapse to make contact with datum feature simulator, or are the simulator fixed at MMB in virtual size? So the simulators are fixed at the virtual size MMB. Then here in this exercise, what is the coaxiality tolerance implied between these two diameters before any geometric call out? So this minus this side, the concentricity will be zero point 0.3 of zero point 0.3, and this side is of zero point 0.2. Mostly we see this concentricity tolerance in pipes or in bearing engineering drawings. Then the next, the large diameter as datum A. So for this, I can say this concentricity of zero point 0.2. This is my datum A. The large diameter A, and here on this side we have to show the runout. Yep, specify a point 1 circular runout to locate the small diameter, and for this arrow for the runout and the zero point 0.1 tolerance with the datum A. So we can show it like this. Then the next is with a circular runout, how much taper on a diameter is allowed on a small diameter. So circular runout doesn't control this taper, so we can say it's 0 here. And if the circular runout specification were replaced with zero point 0.1 total circular runout specification, then the taper will be half of this, which is 0.0. 0.05. If with the circular runout specification, how much circularity on a radius is allowed on a small diameter, it's zero point 0.1. And how much location on a diameter allowed on a small diameter relative to datum A, it will be the same zero point 0.1. Then on the drawing above law, apply a runout requirement to make the left face perpendicular to the datum axis within 0.02. And for this, I can say on this side, uh, the total circular runout symbol with a tolerance of zero point 0.2 with datum A. Then next is what is the technical difference between the runout specifications on two faces. So the circular runout controls the perpendicularity and the wobble of each element, but not the flatness of all over surface. But this total runout, which is here on this side with zero point 0.2, the total runout controls the it's a 3D control, and it requires a total sweep. So it controls the flatness as well as the perpendicularity both. Then here in this workshop exercise, uh, there are three recommended coaxial controls: position, runout, and profile. So answer the question 16 to 18. So the first one is position, and position is axis control or the surface control. So it's location. Position controls the location, and the position controls the orientation. And for this position, we require the size tolerance. Then the runout axis control or the surface control. So runout controls the form, orientation, and runout controls the location as well. And the basic dimension used for diameter or it's a size tolerance required. So for this, the size tolerance required. And the next is profile. Profile controls the form, and profile controls the orientations as well as locations. And the size tolerance is required. Then the next is explain the difference between total runout and the position of a cylindrical part. Assuming the numbers are the same, which is more restrictive requirements. So the total runout controls the form also. So the position of a cylinder doesn't control this form of a cylinder, but it controls only the position. And here in the next 20th question, one of these controls can have a feature modifier, MMC. The answer is MMC, and which two geometric characteristics controls opposite median points of a features are those common controls used in geometric tolerancing. So these are the concentricity and symmetricity. We are not using this um, in the drawings based on GD&T and no feature modifier. So it's concentricity and the this one symmetricity. Then this next exercise is of shims fitting in a floating fasteners assembly. So for MMC of the hole here is 0.290. It's 0.290, and the MMC of the fasteners we know for this 1 by 420 screws given in this book, which is 0.250, and it gives us a size of point zero 0.04. So there are two types of fastener cases. This one is the floating fastener case, and in this case of a floating fasteners, we divide this tolerance in between hole and the threading hole. So 0.20 clearance for this hole and 0.02 tolerance for the fasteners. We divides equally. And in the case of fixed fasteners, we goes with 60-40% or sometimes with 70-30%. And here for this next questions, it's 0.45, and the MMC of the hole is 0.410. The MMC of the fasteners, which is given in this drawing, is 0.375, and it gives us a size of 0.035. And when we split the 60 and 40% in for the hole and for the fastener hole, for the hole I can go with for the fasteners I can go with 1.0.15, and for the hole is 0.02. And then here in this reinforcement exercise, so it's the first one is the flexible tube, and the second is the reinforcement cap. We constrain this flexible tube with this M5 self-threatening screw. So it's a case of this fixed fastener, and this flexible tube comes in the restrained condition after this reinforcement cap. Before that, we have to consider the free state modifier. So on this flat face, I can define the flatness requirement and the free state modifier requirement, and this diameter I can say my primary datum feature. I can say it's my datum, and this 25 diameter I can say it's my datum. Again, I can show this flatness requirement here, and I can go with the profile tolerance on this profile which is inside, and for this tolerance of the size, I can go with this MMC of this flexible tube, which is 26 minus the MMC of this reinforcement cap, the outer diameter, which is of 25.5. So the clearance I will get of zero point 0.5 between the reinforcement cap and the flexible tube. So here it's zero point 0.5, and when I multiply this zero point 0.5 with 2, I will get the 1. Then to position these holes, the MMC of this hole is 4.6 here, and the MMC of this reinforcement cap holes are 6.2. So when we subtract this 4.6 from 6.2, we get 1.6, and this 1.6 clearance we split into hole and in the depth hole. And then here in the next exercise, we have to find out the IB and OB, internal boundary and outer boundaries, for these holes and pins, and these dimensions are regardless of feature size. So for the regardless of feature size, outer boundaries for this hole is of 4.6 plus 4.1, it's 4.7, and the inner boundary is 4.5 minus this zero point 0.1, it's 4.4. And for this pin, the outer boundary is this 11.5 plus zero point 0.6, so 12.1, and the inner boundary is this 11.2 minus zero point 0.6, so 11 point, sorry, 10.6. Then next is for this hole, the outer boundary OB will be this point 8.2 plus 0.35, it's 8.55, and the inner boundary is 8 minus this 0.35, so 7.65. Again for this hole, the OB outer boundary, it's 4.7 plus zero point 0.4, so 5.1, and the inner boundary IB is this 4.5 minus zero point 0.4 is 4.1. Then the next is of this pin, it's 8.2 plus zero point 0.5, 8.7 here, and 7.4 here, 8 minus zero point 0.6, 7.4. And then here in this OB is of 4.6 for this pin, and IB is 3.4. And then here to find out the IB and OB, the condition is of MMC, maximum material condition, here with the tolerance, and to find out the inner boundary and outer boundaries. For the first case, it's MMC for zero point 0.2. For the whole, it's at the 4.5, it's zero point 0.2, and at the 4.6, it's 0.3. So the outer boundary will be 4.6 plus zero point 0.3, and outer boundary is 4.9, and inner boundary is this simple 4.5 minus zero point 0.2. The maximum material condition of this hole is 4.3. So here for this pin, the MMC at this pin, the OB with MMC will be it's this 10.8 plus zero point 0.2, so it's 11, and IB will be this 10.75 minus zero point 0.5 minus zero point 0.7, zero point 0.2 plus zero point 0.5, zero point 0.7, so 10.75 minus 10.7, it's 10.05. Then for this next hole, it's 8.2. The OB is 8.2 plus this 0.15 mmc at this point, at this size. So when 8.2, the mmc will be 0.35. So 8.2 plus 0.35 will give us the OB, which is of 8.35 plus zero point 0.2, 8.55. So OB is here 8.55 in this case, and the IB is this 4.5. This 8 minus 0.15, 7.85. Then next is of 4.5, this hole, and for the hole, at the mmc zero point 0.5, and here it's zero point 0.7, so 4.5, 4.7 plus zero point 0.7 is 5.4 is OB, and the IB for this hole at mmc is 4.5 minus this zero point 0.5, so answer is 4. And for the next, this pin, the size is of 8, and the MMC is 8.2 plus this zero point 0.5, which gives us OB outer boundary, and it's 8.7. And this IB is 7.9 minus this zero point 0.8, so 7.1. And for this next pin, the size is of 4.3 mmc for the OB, 4.3 plus zero point 0.1, it gives a size of 4.4. And here the IB is 4.2 minus zero point 0.2, IB is 4.